The variance of a sum of random variables will be, so the covariance is half the correction factor needed to make the variance of a sum the sum of the variances. It's defined as the expected value of the product of the variations from the mean, but we usually compute it as the difference of the expected value of the product and the product of the expected values. We can also use the properties of the covariance to simplify this computation once we know what those properties are. So first, we note that the variance of x plus y is, and the variance of y plus x is, and they're the same, so the covariance of xy is the same as the covariance of yx. It doesn't matter what order we list the variables. What about the covariance of kxy, where k is some constant? So we have our covariance and our covariance of kxy. And because k is a constant, we can factor it out of the expected value. And we can factor it out of the expression. And the expression inside the parentheses is just the covariance of xy. So if I multiply one of the variables by a constant, that also scales the covariance by the same constant. Now, by the first thing we did, we know that the covariance of xky is the same as the covariance of kyx. We can remove that factor of k, and we can switch the variables again, which means it doesn't matter if we multiply the first or the second by the same constant. And in general, any property we prove involving the first variable will extend to the second variable. Note this is half of the requirement of something to be linear. So let's consider the covariance of a sum. We have the covariance of x plus y, z. By our computing formula, that's the expected value of the product minus the product of the expected values. We can expand that expression, and because expected value is a linear operator, the expected value of a sum is the sum of the expected values. And likewise, and we rearrange our terms a little bit, we have the covariance of x and z plus the covariance of y and z. And that means we can split the sum on the first variable. And again, since it doesn't matter what order we list the variables, this means we can also split on the second variable. For example, let x be the size of a surgical claim and y be the size of the associated hospital claim, where our expected value of x and y and of x squared and y squared are, and the variance of the sum is 8. And let C1 be the size of the combined claims before the application of a 20% surcharge on the hospital portion, and C2 be the size of the combined claims after the application. Find the covariance of C1 and C2. Now, C1 is the sum x plus y, and C2, that's a sum x plus 1.2y. That reflects that 20% surcharge. And so we want to find the covariance of this. So our first argument is a sum, so we can split the covariance. And our second argument is also a sum, so we can split each of these. And it's important to note that we have to do the split separately. Here we have a scale of 1.2, so we can move that factor to the front. Now remember, the covariance of a variable with itself is just the variance, so we get the variance of x, the variance of y. Since we have the expected value of x and x squared, we can find the variance of x, and likewise the variance of y. Remember, the covariance is half the correction factor needed to make the sum of the variances equal to the variance of the sum. So because we know the variance of the sum, the variance of x, and the variance of y, we can compute the covariance. And so we find And substituting in our values gives us